Today we're going to look at lesson 3-3, concavity, and using the second derivative test. So as we look at this diagram, we can actually use our knowledge of increasing and decreasing functions to help us define concavity. So if you recall, we used the first derivative test to determine whether something was increasing or decreasing on the function. So as you can see here, the function is decreasing and then going to increasing. And this is considered concave upward. The graph is opening up. Whereas this is increasing, going to decreasing, and this is considered concave downward. The graph is opening down. Locating the intervals on which the first derivative increases or decreases can determine where the graph of f is curving up or curving downward, and this is formally defined as concavity. Then these are our tests for concavity. So the very first test, really you're just going to find the second derivative. And if you plug in a value, we're going to do some very similar tests as we did with the first derivative. You're going to have intervals, and you're going to choose a value in that interval. If the value of the second derivative is positive, then your graph is going to be concave up. If the value of the second derivative is negative, then the graph will concave down. And so let's add a few things here. So remember, concave up looks like this, and the tangent line would be underneath the graph if it is concave upward. And then for concave downward, your graph would look something like this, and the tangent line would be above that part of the graph. All right, so applying the concavity test. The very first thing you're going to do is locate any x values where the second derivative is equal to 0 or undefined. So this is very similar to what we did when finding critical numbers with the first derivative test. Then you're going to use these x values to determine your intervals on which you're going to test, and then you'll test the sign of the intervals. So as you can see, it's very similar to that first derivative test. For a function that is not continuous, so if it has a point of discontinuity, the test intervals should be formed using those points of discontinuity as well as the points here that you find in this first part of the test. So let's look at example 1. Example 1 has two parts to it, so I'm going to move this over and give us some room. So really the test for concavity is used mostly when you don't have or are not able to draw the graph of the function. But for our purposes here, I want you to see the graph of the function as we're applying the test. So we're going to apply the test as if we don't have the graph, but then I want you to see that graph so that you can determine that yes, the test is true and it's working. So our original function is right here. So this is our original function. And then we're going to start off with finding the first derivative. So the first derivative is just simply 2x and first derivative. And then we're going to find our second derivative. So the second derivative here is just going to be 2. So since 2 is positive, and this was our second derivative, so since 2 is positive, according to the test guidelines that I showed you earlier, this is going to be concave upwards. Think in terms of, how do I remember which is which? Well, if you recall, this is just a simple parabola, and so we were able to tell if a parabola opened up or down if A, the coefficient of the squared term, was positive or negative. If a was positive, it opened upwards towards where numbers are positive. If a was negative, it opened downwards towards where numbers are negative. So same thing here. Our value is just a constant number 2, and it's a positive value of 2. So that means that the second derivative's sign is positive, and that we want that graph to open upward towards positive numbers, so it's concave upward. All right, so let's look at the second part. So as you look at this graph, notice that it's a partial graph because it has a definite beginning. It doesn't go infinitely in both directions, so it definitely starts here and goes infinitely in this direction. But it is actually opening downward. It's curving down. So I anticipate that we should get concavity downward. So this is our original function. I don't like the way that original function is written, so I'm going to rewrite it to where we don't have a radical. So that would be x to the 1/2. And now I'm going to find the first derivative. So I get 1/2 x to the negative 1/2. Because remember, we subtracted 2 halves. We subtracted 1 from there, and that's how I got the negative 1/2. So that's our first derivative. And then we want our second derivative. Apparently JoJo feels the need to bark while I'm trying to teach. Highly distracting. All right, so then I am going to multiply negative 1/2 times 1/2. That is going to give me negative 1/4 x, and then we're going to subtract 2 over 2 from that, and that gives us an exponent of negative 3/2. I don't even have to plug any values into this second derivative. Oh, let's go ahead and write that this was the second derivative. So for our purposes here, this is really in the denominator. It's going to be the cube root of x squared. But the fact that I can't take, well, our second derivative's value right here is going to be negative. We're going to talk about how to find the intervals in a minute, but if you just look at any value that I put in for x, I can only put in positive values for x. So if I can only put in a positive value for x, no matter, and I can only take a square root of a positive number, so this is going to turn out to be positive, but it'll be in the denominator, and the coefficient is negative. So overall, the value of this function is negative. So because it's negative, it is going to be concave downward. And you can see that it's curving downward like this. That would be a concave downward. Okay, for the you try it, you've guessed it, you're going to try it on your own. So pause the video, do what we just did. I did give you a graph, so it's kind of a hint as to what the answer should be, but your work still has to prove it. All right, so pause the video. I said pause the video. Okay, so we are going to find the first derivative. And so that will end up being negative 4x. And then the second derivative is equal to negative 4. So just like example 1a, this is a constant, so the value of that second derivative is always going to be negative. So therefore it will be concave downward. All right, very good. All right, so example 2, this time we have a little bit more involved original function. And so I don't like the way it's written, so I'm going to rewrite it so that it's not a fraction. So f of x, and the numerator stays as a 6, and I'm going to bring all of this up into the numerator. So that means that its exponent, which is currently positive 1, will become a negative 1. So this is my original function. Okay, so then let's find the first derivative. So our first step is to find f prime of x. So because it's got a constant in front of it, I can use the chain rule with the constant rule. So I've got 6 times, and then I'm going to take the derivative of this right here. So the negative 1 is going to come in front. So negative 1 times x squared plus 3, and then reduce that exponent by 1. And then we have to multiply by the derivative of the inside. So we took the derivative of the outside, and the chain rule says you also have to multiply by the derivative of the inside. And so the first derivative looks like negative 12x, x squared plus 3 to the negative 2. So this is our first derivative. But we want the second derivative. This is going to be a little bit more involved. So step 2, actually this was step 1. Make this step 2. So this is going to be step 3. We're going to find our second derivative. So we do have to use the product rule. And the reason is because this is no longer just a constant. So it's got an x attached to it. So it's this times this. So we're going to take and remember, look at this one right here as if it's right here. This is our first function, and this is our second function. So I'm just going to take the first function exactly as it is, but then I'm going to multiply by the derivative of the second function. So the derivative of the second function is negative 2, pulled out in front, x squared plus 3, reduce that exponent by 1, and multiply by the derivative of the inside. Then plus the second term times the derivative of the first term, which is just negative 12. All right, so then this is equal to this first term right here. I'm going to multiply the 12x to the 2 and to the 2x. So negative 12 times negative 2 times positive 2 is going to end up being 48. And then it'll be an x squared times the x squared plus 3 to the negative 3. So that takes care of the first term, plus, actually minus, and the reason why it's minus is because the 12 here is negative. So minus, I'm going to put the 12 in front, x squared plus 3 to the negative 2. All right, we're going to further simplify. I'm going to write this as in its fraction form. So I've got 48x squared over x squared plus 3 raised to the positive 3 minus 12 over x squared plus 3 raised to the second power. So what I would like to do is get this into one fraction. They almost have like denominators. This has the x squared plus 3 cubed, whereas this one has it squared. So if this one had one more x squared plus 3, it would match the cube here. So I'm going to multiply this one by another x squared plus 3, but I also have to multiply the top by another x squared plus 3. So I get 48x squared, and then I'm going to distribute the negative 12 into the parentheses. And so I get negative 12x squared minus 36. Now it's all over that same denominator of x squared plus 3 cubed. Then I can collect like terms. So I end up with an answer of either 36x squared minus 36 over x squared plus 3 cubed, or you can factor the numerator, which would be 36, and if you factor out the 36, you get x squared minus 1, which actually is the difference of two squares, which factors as this. The factoring doesn't actually do us any good, so in my opinion, oh so humble as it may be, let me put this in pink. either one of these two will work. All right, so this becomes our second derivative. That was a long process, but that's why we learned how to find all those derivatives in the previous unit. Okay, so that's only step 3. So we have one more step. Now we're going to use the second derivative in order to find whether our graph and where our graph is concave up or down. But in order to do that, we have to find our interval. So look at this graph or this function. You want to determine where would the function be undefined, because that's a place which will cut our interval, or where the function would be equal to 0. So f of x is actually defined for all real numbers on this function, because if you look at the denominator, which is the only place where we could have a discontinuity, it's x squared plus 3. Well, there's no way for this value here to be 0, because whether x is positive or negative, when you square it, it's going to be positive. And you add a positive value, it's still positive, and cube it, it's still positive. So there is no way for this denominator to be 0. So f, the second derivative, f double prime of x, is defined for all real numbers. Now, the other thing that we have to look at is, where is the second derivative 0? The only way for this fraction to be 0 is if the numerator is 0. So I don't care about the denominator anymore. I only look at this numerator. If I set this numerator equal to 0 and solve for x, I'm going to add a 36, divide by 36, and I end up with x squared equals 1. And if you solve for x squared equals 1, you will get positive and negative 1 for x. So f double prime of x will equal 0 when x is equal to negative 1 and x is equal to 1. So this is where we're going to get our intervals from. So the third step would be our testing intervals. So I'm going to go from negative infinity all the way to positive infinity, but my intervals are going to break here and here. So I'm going to go from negative infinity to negative 1. Then I'm going to break and go from negative 1 to positive 1. And then I'm going to break and go from 1 to infinity. So I'm going to create a table here. And then we're going to choose values in these intervals. You can choose any values you want to, as long as it falls in this interval. I like to choose as small a number as possible and as easy of a number as possible, just like we did before. So in this interval, I'm going to choose x equals negative 2. And in this interval, I'm going to choose x is 0, because that's my favorite. Remember, you can't choose the endpoints ever. You have to choose in between. And then on this, I'm going to choose x equals 2. So when you go and plug in these values, I highly suggest you use probably this fraction right here to put into the y equals of your calculator. When you do that, make sure you're using parentheses. So this has to go in parentheses, then divided by, and then this one can be left just as it is. But make sure that whole numerator gets put in parentheses, otherwise you're not going to get the same values as I get. So let's find the value. Whoops, I already know what I'm plugging in. All right, so I'm going to get these ready. Okay, so I'm going to plug in negative 2, 0, and 2. So all I did was put, as I said before, this into the y equals of my calculator, and I'm going to use the table feature and have it do the work for me. So for this first one, when I plug in negative 2 into the second derivative, I get a positive decimal, 0.3149. And when I plug in 0, I get a negative 1.3 repeating. And when I plug in 2, I get a positive decimal, 0.3149. So my conclusions are going to be, as I look at the sign, and I only really care about the sign. So this one has a sign that is positive. So because it's positive, my graph is going to be concave upward. Shh, hush. They hear sounds from the wind. That's enough. Stop. None too happy. All right. So on our second interval, because the second derivative was negative, we are going to have the graph concave downward. And I'll show you all of these in a minute as soon as we get our conclusion. Dowd. That would be wrong. Can't talk and write at the same time. Downward. And then this last one is positive, and so it is concave upward. Now it is important that in these intervals it goes from positive to negative, from negative to positive, because if it doesn't, these are not, well, I'll tell you what the points are called here shortly, but they're not critical values. We find they're very similar to how we found critical values, but they're actually called inflection points. So for an inflection point to occur, the graph is going to move from upward to downward and vice versa. So because we go from plus to minus and minus to plus, we know we have this change in curve. If it went plus to plus, there would be no change in curve. It would just be concave upward all the way along. So let's go ahead and look at the graph. So our first interval goes from, and I'm going to cut our graph here at our inflection points, which is at -1. So here's -1, and the other one was at +1. So notice that we're not cutting at a relative max or min, not like we did before. Relative max and mins are where you see the graph stop increasing and going to decreasing and vice versa. The inflection points is where the graph stops being concave up or being concave down. Within those intervals of concave up and concave down, there are relative extremas, and we'll talk about that in a minute as well. All right, so this right here, as you can see, if you look at the curve of the graph, it's actually opening up from here to here. So that is concave up. So this is concave upward. I'm just going to put up because I have very little room. And then this one right here, if you just look at the curve of the graph, it's curving down. So that is concave down. Concave downward. I'm just going to put down because I have a short amount of room there. And then this one, as it changes here, it's curving up again. If you can look at that curve, it's slightly curving up. And so based upon our interval, it is concave upward. All right, so time for you to try it on your own. So go ahead and do exactly what we did on the last problem. You want to rewrite the original function to where it's not a fraction. Find your first derivative, find your second derivative, look at that second derivative function, determine where that second derivative is undefined, which would be points of discontinuity, and where it would be 0. Those are going to determine your intervals. Then test your intervals, look at the signs, are they positive or negative, and that will tell you what part of the graph is concave up and concave down. Just looking at the graph the way it is right now, I don't know where the inflection points are. I have to use the second derivative to find those inflection points. All right, so pause the video. You do your thing. Restart the video when you're ready. Okay, so step 1. I'm going to rewrite the original function. So it's still f of x, but you should have rewritten it as 12 times x squared plus 4 to the -1. And then the second step is to find the first derivative, which is -12 x squared plus 4 to the -2. And then, whoops, where did I miss my, oh, I knew I missed something. So I found the derivative of the outside, but I still have to find the derivative of the inside. So remember, the derivative of that inside is times 2x. Aha. So then my second derivative, if I multiply the -12 and the 2x, I get -24x times x squared plus 4 raised to the -2. Now, we need to find our second derivative. So step 3, f double prime of x. So this is going to be my first part of the function, and this is going to be my second. I have to use the product rule. So the product rule says take the first function. Why do I keep wanting to write 12? I don't know. Negative 24x, then times the derivative of the second part of the function. So negative 2 times x squared plus 4 raised to the negative 3, and then don't forget to multiply by the derivative of the inside. And then plus, and I can see on the video I'm going to run out of room, so I'm going to run down here a little bit. So the second function, which is x squared plus 4 to the negative 2 times the derivative of the first function, which is just negative 24. So this equals, if I multiply out negative 24x and negative 2 and 2x, I am going to get a positive 96 x squared plus 4 raised to the negative 3 minus 24 times x squared plus 4 raised to the negative 2. And so now I want to write these as fractions. So 96x squared all over x squared plus 4 raised to the positive 3 minus 24 over x squared plus 4 raised to the positive 2. So now I want common denominators, so I can combine this into one fraction. So this one's missing in x squared plus 4. So I multiply that to top and bottom. And then I'm going to distribute this negative 24 all the way through. So watch your signs. So you get 96x squared minus 24x squared. Those I'll combine in a minute. Minus 96. All divided by x squared plus 4 raised to the third. Okay. Move this up a smidge. And then, combining like terms, I get 72x squared minus 96 all over x squared plus 4 raised to the third. Now, if you factored out the numerator, which would be helpful for when we need to find when the second derivative is 0. So I'm going to factor out that numerator, so or, I guess I can put an or here. You would have, they have a 24 in common, and you would be left with 3x squared minus 4 all over x squared plus 4. Now factoring doesn't do us a whole lot of good, so it doesn't matter which one you have, but this is your second derivative. So now to get to step 4, which is our intervals, how do we find our intervals? Well, sorry for the interruption. The doggies were saying hello to kids across the street. Such excitement for the dogs. All right, so to find my breaks in my interval, I'm going to look at the denominator. Again, just like the previous example that we looked at, example 2, there's no way for the denominator to be 0. So f double prime of x is defined for all real numbers. It is not a discontinuous function. And you can actually see that in the graph above. So what would make it 0? So you can either set the numerator equal to 0 or this one equal to 0. This is the only part that's going to cause the numerator to be 0. And so if I actually took 3x squared minus 4 and set it equal to 0, you get 3x squared equals 4, x squared equals 4 over 3. And then when you take the square root of both sides, remember you have to do positive or negative. And so you end up with x equaling 2 over the square root of 3 and x equaling negative 2 over the square root of 3. So since negative 2 over the square root of 3 is smaller, I'm going to start my interval with that. So here we go. I'm going to go from negative infinity to negative 2 over the square root of 3. And then from negative 2 square root of 3, we're going to go to positive 2 over the square root of 3. And then we're going to go from 2 square root of 3 to positive infinity. And then you're going to choose values in each of those intervals to check, to test. Now, if you take -2 and divide it by the square root of 3, you get like -1.15. So I want to go to the left of -1.15. So I choose -2. That'll make it safe. And then in between these two is going to be 0, so that's easy. And then to the right of 1.15, I'm going to choose 2. So those are the values I'm going to substitute in to my second derivative. Okay, now I put into the y equals in my calculator, I put this in, not this one, because this is easier to put into the y equals. Just make sure that you put parentheses around that whole numerator. All right, so what do we get? So when you substitute that in and use the table feature, you should have gotten a decimal, 0.375, or if you didn't choose -2, you should have gotten a positive value of some sort. And over here, you should have gotten -1.5, or if you didn't choose 0, a negative value of some sort. And then for 2, you should have gotten positive 0.375. So let's make our conclusions. So since this one's positive, it should be concave upward. And then since this one's negative, it is concave downward. And so we have a definite point of inflection because we went from positive to negative. And we have another point of inflection because we went from negative to positive. And this is concave upward. All right, so then let's just go and look at your graph really quick. Oh, wow. Apparently that's not going to move with my graph. Don't let that bother you. All right, so then I'm going to split the graph at approximately -1.15, which is going to be, ooh, I don't know, like right around here, give or take a little bit. -1.15. And then this one's going to be at positive 1.15. So this part of the graph right here is concave upward. This part concave downward. This part concave upward. And these right here are going to be points of inflection, which we'll explore more right now. All right, so let's look at this diagram. And as I was kind of intimating before, these right here are points of inflection. It's where a graph goes from concave up to concave down, or from concave down to concave up. Either one. So your properties of inflection, the only really thing I have to say to this one is A, what a beautiful color that is, and B, how do you find your points of inflection? So it's very similar to how we found our critical numbers. You're just going to use your second derivative test, and we've already talked about it really in the previous example. You're going to figure out when the second derivative is equal to 0 or when the second derivative is undefined. The undefined is going to come from points of discontinuity. All right, so let's look at example 3. It's a little bit funkier looking graph. And the question says, discuss the concavity of the graph of f and its points of inflection. So we need to mention the points of inflection and where the graph is concave up and concave down. So I'm just going to go through our steps. So step 1, we are going to find our first derivative. So we're not doing anything different. This derivative is actually much easier to find than the previous ones that we were doing. All right, so there's your first derivative. And then our second step, find your second derivative. So we get 12x squared plus 6x minus 6. So remember how I told you factoring was vitally important? Well, here it comes back to haunt you again. So in order to figure out, now clearly this is continuous on the entire function because there is no place in this function where it is restricted. So there's no points of discontinuity. In fact, it's a squared function, so we know it's the graph of a parabola. So the question is, where would this become 0? So we're going to let the second derivative be 0, essentially. And we're going to factor it to solve. You're not allowed to throw it in your calculator. You've got to show the algebra. Your calculator is a tool. It's not there to do everything for you. So the first thing I want to do is make it easier on myself. I want to factor out anything that I can. So because it has everything has a 6 in common, I'm going to start by factoring out the 6. And then I'm going to use my swing factoring. So I'm going to multiply the 2 to the negative 1. And then I'm going to ask myself, what factors of 2 subtract to give you 1? Well, there's only one choice, so that would be 2 and 1. And because the middle term is positive, the 2 gets the sign, and then the 1 is negative. But also, because we multiplied by 2, we have to divide out that 2 again. And so our final factoring would be x plus 1, 2x minus 1. So the parts that will make this 0 are going to be set this equal to 0 and this equal to 0 and solve. You will get x equals negative 1 for the first one and x equals positive 1/2. So those are going to become our points of inflection. And we will find, we don't really have to find the order pairs unless the directions ask you to. I'm mostly concerned about the x value. So then we're going to use those values to find our intervals and test them. So our first interval is going to go from negative infinity to negative 1. And then we're going to go from negative 1 to positive 1/2. And then from positive 1/2 to infinity. Create a table of values, and then you choose a value in each of those intervals. In this interval, I choose negative 2. In this one, I choose 0. And in this one, I choose 1. You're going to substitute those values into the second derivative. And again, it's easiest to put that second derivative into the y equals and let your calculator do the work. And then the calculator gave me 30 for this one, negative 6 for this one, and 12 for this one. And so now you're going to evaluate. This is positive, so it's concave upward. This is negative, so it is concave downward. And this is positive, so it is concave upward. Now, how do you write your conclusions? Therefore, the graph is concave upward. Do I have to write it this way? Yes, the graph is concave upward from negative infinity to negative 1, comma, I'm going to move this up a smidge. Much better. Concave downward from negative 1 to 1/2 and concave upward from 1/2 to positive infinity. In addition, told you calculus was a lot of writing. There are points of inflection at x equals negative 1 and x equals 1/2. And you can see that happening here at -1. So we would cut the graph there. And at 1/2, which would be what, right about here? Okay, so from here, the graph is concave up. There's your point of inflection right there. Concave down, there's your point of inflection right there. Concave up. Now this is a relative minimum, and then this is going to be a relative maximum. And then we'll talk about whether it's neither as we go along. There's another relative minimum. Next. All right, so you try this by yourself. Pause the video, do your stuff, and restart the video to check your work. All right, so going as quickly as I can. Your first derivative. And then our second derivative. And then we are going to factor that. Basically, we're going to set it equal to 0. And I'm going to factor out a 12x. And so I get an x squared minus 1, which that is the difference of two squares. So x plus 1, x minus 1. Now, on this one, wait a minute. I forgot. I made a boo-boo. Good thing I caught it before I went further. That's not an x squared. There we go. That's it. All right, so when you divide x squared by x, you should just have x. So if I set this equal to 0, I get 0. It's a monomial. Set this equal to 0, I get 1. So for my third step, I've got x equals 0 and x equals 1. Those are going to set my, for my intervals. I don't like the way that looks. I want to make it pretty. How about again? All right, so from -infinity to 0, from 0 to 1, and from 1 to infinity. Okay, I choose x equals -1. Something in the middle is going to have to be x equals 1/2, and then x equals 2. Substitute those into my second derivative. My calculator is going to help me with that work. And I get 24, -3, and 24. So my conclusions, this one's positive, so concave upward. This one's negative, so concave downward. And this one's positive, so concave upward. Now I'm not going to take the time to write the conclusion. I'm going to read it to you. So your conclusion for the fifth step, you're writing this. I'm not going to take the time on here to write it because you should have already written it. So the graph is concave upward from -infinity to 0, concave downward from 0 to 1, and concave upward from 1 to infinity. In addition, there are points of inflection at 0 and at x equals 0 and at x equals 1. So here's your points of inflection at x equals 0 and x equals 1. So you can see here that the graph is opening up here, concave up, opening down, concave down, opening up. Very good. Okay, so the question here that I have for you, after all is said and done, is it possible for the second derivative to be 0 at a point that is not a point of inflection? So is it possible for the second derivative to be 0 at a point that is not a point of inflection? So for instance, here we have concave down, because it's starting to curve down. This right here, so I'm going to circle it. This right here is going to be a point of inflection. And then we have concave upwards right here. So if the graph goes from concave down and then switches to concave up, then the second derivative does have a value of 0, and in this case 0, 0 is a point of inflection. So yes, this is a point of inflection, but look at this one. The second derivative has a value of 0, but this point, let's circle it, is not a point of inflection because by definition it has to go from concave up to concave down or concave down to concave up. This one's going concave up because it's opening up here, and then concave up again, it's opening up. So it always goes concave up, concave up. The whole graph is concave up. So this is not a point of inflection. It is a relative minimum, but it is not a point of inflection. So you might want to underline that on this one. Is not, is. Well, let's look at the actual picture. All right, so this right here, the second derivative test can also be used to test for relative max and minimum. So at the same time that we're testing for concave up and down, we can test for relative max and minimum. So in this particular case, you can see it's concave down, and this is the highest point, and that will end up being our relative maximum. This is concave up, and this is the lowest point on that graph, so it's going to be a relative minimum. So I'm going to move this over for those of you who are trying to write this down, and you can pause, make it a little bit smaller. You can pause the video to write that down. All right, so basically we're going to end up looking at the second derivative, and if it's positive, remember we know it's opening up, so there should be a minimum. So think of that parabola way back when in algebra 1 and 2. And if the second derivative's interval is negative, then there's a relative maximum, because negative means it's concave down, it's opening down, so it should have a high point. If it's exactly equal to 0 at the second derivative, then the test is going to fail. And you have to look at the first derivative test, so it is important. So we get a relative minimum here, a relative maximum here, but if it's equal to 0, then you have to use that first derivative test to determine whether it is a relative minimum or a maximum or neither. You can't just say, oh, it equals 0, so therefore it's nothing. I mean, it could. So if it fails the second derivative test, you have to go and use the first derivative test. All right, so our last example, and then you have a try it after this. So almost done, hang in there. Okay, got it all in there. All right, so we're gonna find just the relative extrema. So we actually have quite a bit less work because we're just finding the relative max and mins, but we still have to go through a lot of the same tests. So step 1, we're gonna find the first derivative, and this one's pretty simple to find. So we get negative 15 x to the 4th plus 15 x squared, and this is our first derivative. And then our second test, or second step, is our second derivative, and this should be fairly simple to find as well. So we get negative 15. Oh, you know what, before we do that, we do have to find the critical values, because the critical values are going to actually be where our relative max and min are. So at this point, this is a little bit different. So let me erase this. See, that's what you get for taking notes in pen, y'all. Okay, so I want to actually find my critical numbers right here. So I'm going to set this equal to 0, and I'm going to factor. So both of these terms have a 15x squared in common, but I'm going to factor out a negative 15x squared because I want my first term positive. So dividing these two, I get an x squared, and I get minus 1. And so negative 15x squared. This is the difference of two squares. And so therefore the critical numbers are, oops, x equals 0, that's for the monomial negative 15x squared. X equals negative 1, and x equals positive 1. Now I'm going to have to put these in order in my table when I get to that, but we'll get to that in a minute. So then we found our critical numbers. Now we want to find, so this was our step 2, finding our critical numbers. So step 3, now we're going to find the second derivative. And so when I do that, I'm just going to use this one. This one would be way too complicated. So now I get negative 60 x to the third plus 30x. All right, so here's why we had to find both the first and second. So for our fourth step, I need to find my points. JoJo's saying hello to the neighbors again. So I need to find the values of my critical numbers. So these critical numbers that I found, I need to find them on the graph itself right here. So this graph remembers the original function. So I'm going to take these and substitute them into the original function. So off the side, I'm going to find the value of those three numbers. So I'm going to put in, I want to put them in order. So negative 1, 0, and 1. So if I substitute these values into the original function, when I put 0 in, I'm going to obviously get 0. Well, since I did that one first, I'll do that one down here. And then if I substitute in negative 1, I get negative 2. And substitute in 1, I get positive 2. All right, so that's going to be important here in a minute because when I set up my table, the table is going to look different this time. We're going to have the point on the original graph followed by the sign of the second derivative, because we really only care about the sign, and then our conclusion. And I'll let you leave the conclusion of the table on this one. So our point we're going to get from over here. So at negative 1, I got a value of 2. So negative 1, I got a value of negative 2. At 0, I got a value of 0. And at 1, I got a value of 2. All right, so then we're going to substitute into the second derivative those x values. Okay. So same x values. All right, but when I substitute in, this time I'm subbing into here. So you can throw that into the y equals of your calculator, make quick work of it. So then negative 1 will give us 30. 0 still gives us 0. And 1 gives us negative 30. So for here, we got a positive value. 30 is positive. So because it's positive, the graph is opening up, so it's concave upward, so it should have a minimum. So this is a relative minimum. This one here, I'm skipping the middle one for a minute. This one here is negative, so the graph is concave downward, so it's opening down, so you should have a relative maximum. And the relative minimum and relative maximums are happening at these points here. But this is 0. So the test fails. So go ahead and write here, test fails. Because the test fails, you have to apply the first derivative test. So if I go to the first derivative and plug in 0 into here, it also equals 0. So it fails the first derivative test as well. It's neither positive nor negative. And so our conclusion for this one is it's neither a relative max or relative min. So let's look at the graph and see, is that true? So the first ordered pair, I'm going to put in my ordered pairs. So the first one is at -1, -2. So -1, -2 is right here. You can see that that's a minimum, it's at the bottom. The other one is at 1, 2. So it's right here, and that's at the top, so that's a maximum. But then the middle one right here at 0, 0, it is neither a minimum or a maximum. It is an inflection point because you can see that the graph is going from concave upward or concave downward here to concave upward. So this is an inflection point, but it's not a relative max or min. It's not at the top of an arc or at the bottom of an arc at all. So these are your conclusions. That's it. So you've got one more to do on your own. Let's see if you have this process down. Here you go. All right, you try. Pause the video, you do your thing, and then restart that video and look to see if your answer is correct. Okay, so step 1, you should have found the first derivative, which was easy. Then from there, you want to find your critical numbers. So we're going to set this equal to 0, and we are going to factor. So each term has a 4x squared in common. That leaves us with an x minus 3. And so if you set each of those factors equal to 0, your critical numbers are, get a good color, therefore your critical numbers are x equals 0 and x equals 3. Okay, so then somewhere off to the side, I'm going to find where those ordered pairs are. Okay, so I only have 2 points this time. So I'm going to put in 0 and 3 into the original function, not the derivative. And so if you put them into the original function, you get 1 and -26. So you can see on the graph that I really had to squeeze the graph in here in order to get that. Here's this 3, -26. Okay, and then here's the 0, 1 right here. So then step 2. Oh, this was step 2. Step 3 is our table. So let's go ahead and put in our point, and then our sign, and then our conclusion. All right, so our first ordered pair is 0, 1. And our second ordered pair is 3, -26. All right. All right, so then I substituted 0 and 3 into, oh shoot, I did not find the second derivative, so let's quickly find it. That would be tough to plug it in if I didn't find it. So the second derivative is 12x squared minus 24x. You probably thought I was going to skip that. There it is. So I'm going to plug 0 and 3 into that, and I get 0 and also 36. So my conclusion is the test fails here. Test fails here. So because the test fails, you have to go back into the first derivative and plug in 0 here. Because f prime of 0 is also 0, the test fails there. And so your conclusion to this one is neither, because both tests failed. And then on this one, it is positive. So because it's positive, that means it is concave upward. And if it's concave upward, you have a minimum, so it is a relative minimum. There you go. Well done. Good luck on your homework.